This is Forge, a 3D game engine, and I barely wrote a line of it myself. An AI did. I designed it, I directed it, but the code? Almost all of it was written by a model, one session at a time. An engine is really 5 systems working together: rendering, physics, the editor, scripting, and the build system. Over this series, I'm going to open up every single one and show you how it actually works. No hand waving, the real thing. Let's start at the beginning. What a game engine even is. So, what even is a game engine? The clearest way to picture it is a kitchen. A game is a meal. The engine is the kitchen you cook it in. You build the kitchen once, the ovens, the counters, the tools, and then you can cook almost any meal you want inside it. That's the whole idea. The engine stays the same. The game you build on top of it changes. So when I say I built Forge, I don't mean I built one game. I built the kitchen, the reusable machine underneath every game. And that machine is 5 systems. The renderer draws the world to the screen. Physics moves things and handles collisions. The editor lets me build levels visually. Scripting runs gameplay logic without recompiling the whole engine. And the build system turns 342 separate files into one running program. 5 systems. Get all 5 talking to each other, and you have an engine. Let's take them one at a time. Here's a confession. For the first 2 days of this project, I built it the dumbest way possible. I'd ask the AI for a file in a chat window, and then I'd copy the code out by hand, paste it into my editor, save it, and go back for the next one. Over and over. By the time I stopped, I pasted more than 200 files by hand. 200. And then I found the setting I'd completely missed. You can select the model, this one's called Fable, right inside Claude Code. And once it's running there, it doesn't hand you code to paste. It writes straight to the file itself. Here's the real thing. Claude Code running on Fable 5, and switching to it is one line. You just tell it which brain to use, right in the chat bar. That's the whole change. Think about the difference. Copy-pasting is like dictating a letter, word by word, and writing everyone down yourself. This is handing over the keys. It writes the file, it runs the compiler, it reads the error that comes back, and it fixes it on its own while I watch the files appear. That one setting, the one I ignored for 2 days, it saved me about a week. So from here on, this is how the whole engine gets built. Everything you see in a game starts as a triangle. So the first real question is, how does a triangle become a picture on your screen? You feed in 3 corner points, 3 vertices, and you get back a shape filled with colored pixels. The thing that does that is the graphics pipeline, and it works like a factory line. First stage, the vertex step places each corner, turning 3D positions into 2D screen positions. Second, the rasterizer figures out which pixels actually fall inside the triangle. Third, the fragment step paints every one of those pixels. And finally, the frame buffer swaps the finished image onto your monitor 60 times a second. So here's the very first thing the engine ever drew. A single cube. No lighting yet. But it's real 3D geometry, rotating in space. Then you give each corner its own color, and the fragment shader blends smoothly across everything in between. Add proper lighting and shading, and you get a real, solid-looking cube. Put it down on a floor, and it casts an actual shadow. That's real depth being calculated, not a flat trick painted on. Now here's the part I don't want to skip. There are two ways to talk to a graphics card. OpenGL is the easy one. The driver hides most of the machinery, and a triangle takes maybe 50 lines. I went the other way. I used Vulkan, where you manage the memory and the timing yourself. The same triangle takes closer to 1,000 lines of setup. More control, more speed, and a lot more room to get it wrong. And every single one of those lines was written by the AI, one session at a time. Here's something people forget. Source code isn't a program yet. It's just text. Something has to take all of it in Forge, 342 separate pieces of source, and turn it into one app you can actually run. That job takes two tools. The first is CMake. Think of it as the architect. It reads your whole project and writes a precise blueprint of what depends on what. The editor needs the renderer. The renderer needs the Vulkan loader, and so on. The second is Ninja, the construction crew. It reads that blueprint and builds everything, fast, only redoing the parts that actually changed. And it runs the compiler, over and over, 342 times. Each of those is a target, one library or one program. The Vulkan loader is a target. The physics library, ImGui, the editor, the game itself. And they don't build in any order. They stack in a dependency graph. Foundations first, then the things that sit on top of them. Which is exactly where it gets fragile. If one foundation fails to build, everything stacked above it fails with it. And it is not instant. You sit there and watch the clock run. This is 20 real minutes of building, squeezed down to 15 seconds. And when it breaks, this is what 342 could take it down. Actually looks like. Presets in the wrong directory, and Ninja quietly reporting that the whole build just failed. Physics is basically a referee for the laws of your world. Every frame, about every 16 milliseconds, 60 times a second, it rechecks everything that's moving and asks two questions. Is anything touching? And if so, what should happen? It answers those in 3 passes. The broad phase is a cheap first guess. Draw a rough box around everything and ask which pairs might be touching. The narrow phase does the exact math on just those pairs. Are they really overlapping? And the solver does the actual work, pushing objects apart, applying the impulse so a box lands or a ball bounces. Watch one crate hit one plate. The rough boxes light up. That's the broad phase. A spark at the contact point. That's the narrow phase. And then it settles. That's the solver. And here it is for real. A crate dropped onto the floor, landing and settling exactly the way it should. Jolt solved that contact. Now, could I have written this myself? Technically. But stable physics is brutal. Jitter. Objects tunneling straight through each other. Stacks that refuse to stay still. So I didn't. I used Jolt, a battle-tested engine that ships in games like Horizon Forbidden West. To build tools for your engine, you need a user interface. Buttons, sliders, panels, and there are 2 ways to build one. Most apps use what's called retained mode. You create a button once as an object that lives in memory, and you poke at it whenever something changes. It's like a filing cabinet you have to maintain, and its state can quietly drift out of sync with your actual game. A game editor uses the opposite, and it's the surprising one: immediate mode. Every single frame, you just say, draw a button here. Nothing persists. The whole interface is wiped and redrawn 60 times a second, like a whiteboard. Which sounds wasteful until you realize it means the UI is always perfectly in sync with your live data. One line of code is one new control. Drag it, and the scene reacts instantly. This is Forge's real editor, and every panel you're looking at is a library called Dear ImGui, including the menu here that shows the live scene tree. That's why almost every engine's editor works this way. No stale state to chase, and I can add a whole debug panel in seconds. Here's a strange question. Why does the engine speak a second language? The engine itself is written in C++. That's the engine block. Powerful, but heavy. Every time I want to change a bit of gameplay in C++, I have to recompile all 342 targets and wait. So the engine also speaks Lua, a small, simple scripting language that acts like a remote control. The C++ exposes a set of functions. Spawn something, run this when a player enters, and Lua calls them. Change the C++, and you're recompiling for minutes. Change the Lua, and it just runs. Instantly. That buys me two things. Speed. I can try an idea in seconds instead of waiting on rebuilds. And safety. I can script a whole puzzle without ever being able to crash the underlying engine. And here it is for real. One Lua file spawning this entire scene as it runs. That's the payoff. Later in the series, I basically write a whole game in 4 words. Plate, door, laser, glass. Because all of the logic lives up here, in Lua, where I can change it as fast as I can think. After all 342 targets fought me, it finally opened. Blank. Ugly. And completely alive. Then I built a game out of 4 simple rules. A plate, a pressure trigger, step on it, and the physics system fires an event. A door. Lua hears that event and tells the renderer to move the mesh out of the way. A laser. A raycast fired straight through the physics world. And glass? It blocks you, but not the laser. Because they're on different collision layers. 4 rules. Now combine them, and you get a puzzle that solves itself. A box slides onto the plate opens the door, and the laser fires through the gap and straight through the glass. The renderer, physics, and scripting all cooperating. From those pieces I built 40 puzzles, and all 40 are written in Lua, running inside the engine I built. Here's every level, start to finish, in one run. 40 puzzles, 1 engine. All of it stitched together from the 5 systems we just walked through, and almost every line of it written by an AI. So that's the whole machine. 5 systems, rendering, the build, physics, the editor, and scripting, working together as one engine. And an AI wrote almost all of it, 1 session at a time. But here's the thing I keep coming back to. Understanding how the pieces fit together is still the job. The AI writes the code. Knowing what to ask for and why is on me. That's what this whole series is about. Next, in part 2, actually shipping those 40 puzzles, and the first real bug that nearly ended the entire project. This is compile error. The build continues,